Okay, we're picking up where we left off in the previous video, talking about the precise definition of the limit. In the previous video, we discussed in a lot of detail exactly what the precise definition of the limit is, both conceptually and mathematically. And so now in this video, what we're going to do is we're going to work some examples. And also in the process, we'll talk about the precise definition of one-sided limits and infinite limits. But the definitions of one-sided limits and infinite limits are just offshoots of what we learned in the previous video. So just simple extensions of the precise definition of the general two-sided limit. So, okay, let's look at this example 1 here. We've got this polynomial function, third-order polynomial, the limit as x approaches 1 of f of x. We know that since this is a polynomial, we could use direct substitution here. So just plug in 1 into f of x, simplify, and you get 2. So this limit, the limit as x approaches 1 of this function, is equal to 2. So now what they want us to do is they want us to think about the precise definition of this limit by analyzing if epsilon is equal to 0.2, then what would delta be? And they want us to do this graphically. So, okay, here's the graph of this polynomial, this third-order polynomial. And the idea is, so, okay, they state the problem here. Here's the two inequalities that are associated with the definition of any limit. So what we're given is, okay, if the output inequality, if we're saying that the epsilon is 0.2, then what must that mean that the delta is? What's the delta that's going to correspond to epsilon being 0.2 for this limit here? Okay, and so what they did is here's f of x, here's the limit value 2, here's the epsilon is equal to 0.2, and then over here we've got x minus a, and with a being 1, right? So this is all based on the precise definition of any limit. We've got the limit as x approaches 1 of the third-order polynomial is equal to 2. Okay, and then we just wrote out the corresponding precise definition of the limit inequalities. These two inequalities need to be simultaneously satisfied in order for this statement, this limit statement, to be true. Okay, but we're at the moment for this example, we're actually not looking at this in complete general. We're not proving this for any epsilon and for any delta. Right now, we're just getting a feel for this by saying, okay, if epsilon is 0.2, then what is delta? All right. The idea is we can think about the output inequality here. So if you simplify this inequality, you get this compound inequality here. And this makes sense because all this absolute value inequality is saying is that we're thinking about an interval with respect to the outputs of the function, right? These three terms are the function f of x. We're thinking about an interval of outputs that are above and below an output of 2, right? The difference between the function and 2, but the absolute value in either direction. But the distance above or below that value of 2 is less than 0.2, right? So that's what this compound inequality is saying. The function f of x in the middle, there's f of x. All of the outputs of f of x that are less than 2.2 or greater than 1.8, plus or minus 0.2 from 2. Okay, but now graphically, though, what we do is we zoom in to this region of the graph that's associated with x equal to 1. So this region here. And that's what they do here. Right here, we're going from 0.8 to 1.2. And we're doing this because this is all we're concerned with. As far as this limit here, it's this region of the graph is all we're concerned with. The limit has nothing to do with anything that's happening out here for this function, right? Now, so around x equals 1, the question is, what is the symmetric distance above and below x is equal to 1 that corresponds to the function output differing from L is equal to 2 by no more than 0.2 on either side? Okay, now note, though, that in this case, we are thinking about the function output differing from 2 by no more than 0.2 on either side of the output value 2, so from both above and below 2. But remember, just note that for another limit, this doesn't have to be the case. When it comes to the limit value being approached by the outputs, you don't have to be sandwiching the output from above and below. It could be the case that the epsilon just corresponds to you're closing in on the limit value from one side, just above or just below. But in this case, it's both sides, right? For the limit as x approaches 0 of sine of x over x, if this is 1, well, approaching 0 from both sides, the graph is doing something like this. And so you could still, for a limit like this, you could still be, given an epsilon of 0.2, in which case you're only, that epsilon is corresponding to just a gap like this, and it's just shrinking, getting smaller and smaller. Well, if the epsilon is fixed, it's not, but so if the epsilon is fixed, if this was 0.2, you would be being asked, okay, well, what is this delta here? It would be like this. If that's 0.2, then what is this delta, is what you would be being asked. You say, okay, so looking at the function, again, in this region here, it's clear that what we can do is we can plot the horizontal lines corresponding to the outputs of 1.8 and 2.2, and that's what they do. And then graphically, they determine the x values corresponding to where the function intersects these horizontal lines. And they get that this is 0.92 and this x value is 1.12. Okay, so now, but what's the delta value? That's what we're being asked, right? According to the precise definition of the limit, if we set epsilon equal to 0.2, then what's delta? What's the corresponding delta? Well, delta is a symmetric value about the limit point, but we can see here that these two x values this isn't symmetric about the limit point. This value is a little bit closer than this value, but that's not a problem. We can still answer the question because we just choose the smallest distance of either of these points from the limit point, which is over here, the 0.92. So 0.92 is 0.08 away from 1, so we just go 0.08 above 1 as well, so it would be like here. And so there's the delta. Well, this would be delta, 0.08. And so the new horizontal line from below would be here. But like, okay, this answers the question. With delta equal to 0.08, the question is answered. If you're 0.08 units from 1 on either side of 1, then the outputs of the function are going to be within 0.2 of the limit value L is equal to 2. But if you increased delta any more past 0.08, then that epsilon, you would go past 0.2. The epsilon would go past 0.2 because this top line would go up a little bit. Okay, but now in the next example, we're going to do an official limit proof. Here, we just looked at a case for a specific epsilon and delta for a limit. And at the start of this section, in the previous video, we did do an official full proof of a limit. However, there was this step here where it was said that, notice if, and they set the value of delta equal to 0.05, which was a key step in this process, but we don't know how the textbook came up with this number for delta. How did they come up with this guess here for delta? So, okay. In the next example, it says that if we've got the limit as x approaches 3 of the function 4x minus 5, and this limit is equal to 7. Well, we know based on the limit laws and the direct substitution property that 7 is correct. 7 is the exact value of this limit. because this is a polynomial function, which applies to the direct substitution property. So you just plug 3 in to f of x here. 4 times 3 is 12, minus 5 is 7. But now in this example, what we want to do is we want to prove, according to the precise definition of the limit, that this is true, that this limit, the limit as x approaches 3 of 4x minus 5, is equal to 7. But like, again, just note that we didn't prove, in this example, we didn't prove that this limit was equal to 2. This limit as x approaches 1 of this f of x is equal to 2. We didn't prove that officially here. We just looked at an example that if the epsilon in the whole precise definition of the limit inequalities, if the epsilon was equal to 0.2, then what is the delta equal to? We didn't show that for absolutely any delta that you pick, there is going to be some epsilon that is constraining the distance of the function value from the limit point for any delta, right? And that's what you need to do in order to officially prove a limit, okay? So that's what we're going to do here. All right, so there's 2 steps to doing a limit proof like this. If we jump ahead to this paragraph on the next page, it says that typical of much of mathematics, sometimes it is necessary to first make an intelligent guess about the answer to a problem and then prove the guess is correct. And that's what we're going to do for these limit proofs. We start by coming up with a guess for delta. Now, but the key is our guess for delta is going to be in terms of epsilon. Okay, remember, to prove a limit, we need to prove the limit definition conditions for all possible values of delta or epsilon. All possible values meaning to where delta and epsilon are any real numbers greater than 0. And so this is why, in order to do this proof, you're going to see how our guess for delta is going to need to be in terms of epsilon. You'll see why this has to be the case in a second. So how do we come up with a guess for delta? And just to clarify exactly what is meant by a guess for delta, if we come back to the precise definition of the limit, so in order to satisfy these conditions, what we're doing is, for this limit, these are the conditions that need to be satisfied based on a certain limit. For that limit to be true, these conditions need to be satisfied. That's what we're trying to prove in this example problem here. Prove that those conditions of those inequalities are true for this limit. We're starting out by, we want to guess a value of delta that will make all of this true. Here, they've just stated the 2 inequalities of the precise definition. These 2 inequalities, that they've just written those 2 inequalities out for this specific limit, right? Here's A, here's f of x, here's L. We're trying to guess a value of delta that's going to need to be in terms of epsilon that will make both of these true at the same time. If we can show that that's the case, well, then because we can pick any value of delta we want, as long as it's greater than 0, then okay, we've proved the limit. Because then we could make delta 0.000 a quintillion zeros 1, and we can state that there's going to be an epsilon then that corresponds to that delta. And so again, how do we guess a value for delta? Well, what we're going to do is we're going to manipulate the output inequality here. Manipulate this inequality as much as we can without changing the inequality to the point where we can relate the output inequality in some way to the input inequality. Okay, so let's take this absolute value expression and bring it here, okay? And now they're going to start to simplify this. So you subtract the 5 and the 7, you get absolute value 4x minus 12. You can factor out the 4 from 4x minus 12. Now you can take the 4 out of the absolute value, okay? So now we're here. And there we go. So we've got now an absolute value of x minus 3, which is the absolute value expression term in the input value inequality. So we've related this expression to this expression. Okay, and so now they can update then these requirements. So we haven't changed the input, but now the output is given by 4 times the absolute value of x minus 3 is less than epsilon. All right, but now you can divide both sides of this inequality by 4. 4 is just a positive number, so you don't have to flip the inequality. So now we're here. We've gone from here to here. These two pairs of inequalities are equivalent. Okay, so now, but what's more useful about this? We converted this inequality here. So how can we use this? Well, again, the main idea is we've got a direct relation of the output and the input inequality. We've got the absolute value of x minus 3 here and the absolute value of x minus 3 here. And this is useful because what this suggests is that we should guess a value of delta that's equal to epsilon divided by 4. If it's saying that if we guess that delta is epsilon divided by 4, then that will satisfy these restrictions here for all delta and epsilon. Okay, but why is it clear that this is what we should guess for delta? Well, because remember, on the right here, this inequality on the right, it visually looks like it sort of is directly related to the input inequality. They look the same, but they're not related at all. These two are the exact same inequality. All we've done is just algebraically manipulate this inequality, right, without changing the inequality. This is still based on epsilon, the deviation of the function from the limit value. But like this looks weird because we don't see any f of x in here. But f of x is still built in here. We just can't visually see it, right? Compared to how this inequality is originally written, we could see the f of x. We plug in x, there's f of x, and we subtract that from L. Well, we're still doing the same thing here. This has just been algebraically manipulated a little bit. This is when you plug in x here, the absolute value of x minus 3, this is still the distance of f of x from 7 as an absolute value. Okay, but what's useful, though, is because this is the absolute value of x minus 3 on the left side here, and we got that same expression for the input inequality on the left side of delta, well, then what that means is that if we say that delta is equal to epsilon divided by 4, what does that mean? Well, what that means is that if we say that the absolute value of x minus 3 is always less than delta, well, then since delta is epsilon divided by 4, well, then obviously this inequality here is always going to be true. This is always going to be less than epsilon divided by 4 as well. And I know this might seem weird to say. It sounds like I'm double talking. But remember, this is really this. We can really come back to this original statement here. This just original straight from the precise definition of the limit, stating the two inequalities. What we're saying is that if we say that delta is epsilon divided by 4, assuming that this input inequality is true, where with delta being epsilon divided by 4, and this is going to be true because this is a statement we make. This is like a definition that it's part of the problem statement. Okay, so if we say that this is, the input restriction is based in that delta is epsilon divided by 4, then this is true. This, exactly as it's stated, is true. Why? Because these two inequalities are the exact same inequality. Okay, so, but coming back to the flow of the main problem, so that's at least what our guess for delta is going to be, epsilon divided by 4. We just came up with a guess for delta. So with that guess, what we do next is prove that this guess for delta does work, which we pretty much just did verbally, but it's like a formality to go ahead and write it out and show how it officially works. So, okay, they say that we're guessing that delta is equal to epsilon divided by 4. Now, from there, they take the output absolute value expression that needs to be less than epsilon, right? If delta is equal to epsilon by 4, then we need to prove that this is true, right? We can pick any value of delta we want, and just this needs to be true. But, okay, like how do we show that this is true officially? Well, okay, if the delta that we pick, that we guess is in terms of epsilon, and then we also show that with that guess for delta that this as it's shown is true, well then, okay, we're done because we can just pick any value of epsilon we want for delta. Okay, and so again, if delta is equal to epsilon divided by 4, You take this expression here, and so there's the absolute value expression. They subtract the 5 and the 7, factor out the 4 from the absolute value. Now 4 times the absolute value of x minus 3, you're multiplying this entire inequality by 4, right, without changing the inequality, and you get 4 times the absolute value of x minus 3 is less than 4 delta. Well, delta is epsilon divided by 4, so plug delta in. This simplifies to epsilon. There you go. This expression is less than epsilon. Okay, but again, you might be scratching your head thinking, so how does this prove the limit? Okay, this proves the limit because we know that the only restriction on epsilon is that epsilon must be greater than 0. Any positive number, absolutely any number whatsoever on the real number line that's greater than 0 applies to epsilon. So this epsilon could be 0.0000500 quintillion zeros 1. And then we know that the delta value that corresponds to this epsilon is just going to be that epsilon value divided by 4. That's the big key. That's where the whole infinitely powerful calculator idea comes in. It's because we just proved all of the precise definition of the limit constraints for any value of the variable epsilon, to where epsilon is any value on the real number line that's greater than 0. And so we can get however close we possibly want to either the limit point A or the limit value L by just picking a value of epsilon. Okay, and so now this still might be a little confusing to you. You might be wondering, why did we need to go through this whole process to prove this? Well, okay, because beforehand, so we had the statement of the limit and what the limit was equal to. Then from there, we wrote out the two inequalities that are based on the precise definition of the limit. And then there's also that delta is any number greater than 0, and epsilon is any other number greater than 0. Okay, so at this step, the issue is we've got two variables, delta and epsilon. It's not an issue at all to make the first statement, the statement which just constricts the input x values. We talked about this in the previous video. There's nothing special about making a statement of how you're sectioning out a portion of the number line for analysis. That's all that's being done here. You're just saying, look, consider only the x values on the number line that are no farther above or below A, the limit point A, than delta, but also not including A itself, right? And then just delta is any number that you want that's greater than 0. We don't have to prove this. This is a statement we're making. This is part of the problem statement. And so the big idea is that, okay, with this restriction applied to the input x values, we're also at the same time making this statement over here. In order for the original limit statement to be precisely true, we need both of these inequalities to be true at the same time. Yes, if these didn't need to be true at the same time, then we could make this statement on its own as well. This would sort of be like part of the problem statement if these were completely independent. But no, we start with this statement that we make, and now since this needs to be true simultaneously with this, well, now this is dependent on this. So with any of these x values constrained by delta, if you plug any of those x values into this inequality, is it the case that there is an upper ceiling on this absolute value expression here given by some random number epsilon? It could be any number, as long as it is a single number. That's a ceiling on this. Well, we don't know. Maybe there is, maybe there isn't. That's what we need to prove. We need to prove that that is the case. If we can show that that is the case, then we can prove the limit, right? And so that's the whole purpose of the proof. That's what we did in the proof. Now, we did this from sort of the opposite direction, starting with the output inequality, and then the final answer was stated in terms of epsilon, but that doesn't matter. It's all the same idea, but like we could state this proof in terms of delta first, which I find more intuitive. So the statement is, in that case, is that the limit as x approaches 3 of the function 4x minus 5 is equal to 7, according to the precise definition of the limit, because if we rope off an interval of x values that are surrounding the number 3 on the number line, and these x values are equidistant above and below 3, with the distance above and below 3 given by any number delta you want, as long as it's positive. And then also this interval of x values doesn't include 3 itself. Okay, it doesn't matter what delta is, as long as delta is any number you possibly want that's positive. Okay, so we've roped off those x values. Okay, then if you took absolutely any of those x values and you plugged them into this inequality, so like into the function, and then found the absolute positive distance of the function output to the output value 7 for absolutely any of the x values you choose from the input interval that was roped off, you will never find an absolute difference of the function value from 7 that is equal to or greater than epsilon to where, and this is the most important part, to where epsilon is equal to 4 times whatever delta value you picked, or whatever delta is, and delta can be whatever you want. That's the big key, that final statement. That's the whole proof, that final statement. It all comes down to saying to where epsilon is 4 times delta. That's the big proof, because with that, then you can pick any delta you want. It doesn't matter. That's part of the problem statement, right? But just stating then epsilon over here, because this inequality is dependent on this inequality, you can't look at epsilon initially as part of the problem statement. You don't know if this is true or not. Yeah, there might be an upper limit like this epsilon. It just depends on what delta is, right? But once you say that, once you mathematically prove that epsilon is something in terms of delta, well then okay, then all right, this delta is part of the problem statement, and so whatever delta you picked, that's going to constrain this. And so you can officially just pick delta however small you want it to be, get however close to the input point you want to get to, and at the same time however close to the sandwiching or constraining the output, the limit value you want, right? Because delta is absolutely any number that's positive, 0.000 500 quintillion zeros 1, and then this is going to be 4 times 0.000 500 quintillion zeros 1. Okay, so next, they give the precise definition of one-sided limits. Now, these are just a simple extension of the general precise definition of the limit, the two-sided limit. Because, okay, before even reading these definitions, we can make an educated guess on what the restrictions are going to be, right? So, okay, what is the precise meaning of the limit as x approaches a from the left of f of x is equal to L? Without looking at the constraints for this L to truly be the limit, this one-sided limit here, this left-handed limit, what would we guess are these constraints? Okay, so first, what's the delta going to be in this case? We're going to have some delta that's greater than 0, okay? So, all right, then, so delta is just roping off the input points, right, that we're considering near the limit point. So what's the interval near the limit point going to be in this case? Well, all right, it's a one-sided limit. That's what a one-sided limit is all about. We're only considering what the function is doing when x is near the limit point a on just one side of a. In this case, this is a left-handed limit, so we're below a. Therefore, the delta restriction is going to be that we're roping off all x values that are within delta below a. This interval isn't including a itself, and also it's an open interval. So how do we write the inequality for delta? Well, because this is a one-sided limit, we aren't going to use an absolute value, because the whole purpose of the absolute value was to make the statement that x could be either above or below a. Okay, so here we just say that we're roping off x values that are less than or equal to, or just less than a, so not equal to a. Anything less than a, it's left-handed limit. Okay, now what's the lower restriction? The lower bound on x? Well, okay, just anything that's delta below a, but not including, it's an open interval, so not less than or equal to. That's it. We've roped off the x values. X is not equal to a, and then it's all x values below a, delta below a, and we just keep it as an open interval. So we don't put equals, we don't do this. Okay, so there's the delta inequality. Now, what's the corresponding output inequality that needs to be satisfied at the same time for this limit to be as stated here? Well, it's going to be, if you think about it, it's going to be the exact same inequality as what we just had for the general two-sided limit, right? For the general limit, it was just the absolute value of f of x minus L needs to be less than epsilon. Nothing's going to change in this regard, right? So, but why not? Shouldn't it be the case that since we're only approaching x from one side, we're only going to be approaching the limit value L from one side as well? Well, no. First of all, we don't know if, let's say that this is A. Okay, so we're coming from below. Let me do this. Let's say this is the limit value L. Okay, the function could be coming in like this. From the left side of A, it could be coming in like this, or it could be doing something like this. We have no idea, right? So if we were coming from above, then f of x minus L is going to be positive. If we're coming from below, f of x minus L is going to be negative. If we're doing this, f of x minus L is going to be positive and negative. So we need to just leave it as the absolute value. And we're thinking about some a positive number epsilon. It's a ceiling on the deviation of the function from the limit value as we get near a from the left. But here, there's with the input restriction, there's no absolute value because we're 100% never going to have the input x values be above a. We'll never be over here. We're only considering the x values being input into the function that are coming from below a. You see? And so there you go. There's the two inequalities for the left-handed limit, and that's exactly what they show here. This is just saying that based on a left-handed limit, so the limit as x approaches a from the left of f of x is equal to L. If this limit statement is true, then these two inequalities must be simultaneously true. And what these inequalities mean is that you can get as close as you want to the limit point A, but only thinking about getting close to that limit point A on the input side below A, coming from below A. You think about input values x getting closer and closer and closer to the limit point A from below A, as close as you want. Delta can be whatever you want. And then at the same time, as you do this, the output of the function is going to be getting closer and closer and closer to the limit value L. But you can get as close from either perspective as you want. You can do this at the same time. Get closer and closer and closer to A from below A, delta close. And then you'll be a corresponding epsilon close to the output being to L. Okay, and then the right-handed limit is the exact same idea. It's the exact same output interval. Okay, and then the right-handed limit is the exact same idea as the left-handed limit. You have the exact same output inequality. It's just that the input inequality is roping off x values from above the limit point, right? Any x that's greater than a but not equal to a, and less than but not equal to delta away from a. It's the same exact idea. Okay, so if we look at this next example, we have the limit as x approaches 0 from the right of the principal square root of x is equal to 0. Okay, well, we know how this limit is determined via the limit laws of the previous section, right? If we come back to the previous section, here's one of the limit laws that we learned. So if you've got the limit as x approaches a of the nth principal root of a function, you can take that nth principal root outside of the limit. And so here we've got the second principal root, right? And the function is just x. So we could take the principal square root out of the limit, and then what we're left with under the root is the limit as x approaches 0 from the right of just x. But x is just a polynomial, so we can do a direct plug-in there, and you get 0, and so now the principal square root of 0 is 0. But we also do have a law for this case as well here. So the limit as x approaches a of the principal nth root of x is equal to the principal nth root of a. So we could have just said the principal square root of 0. Or once we took the principal square root out of the limit, we could have just come here. The limit as x approaches a of x is equal to a. Okay, but you might be wondering, though, how are we applying these limit laws to a one-sided limit, right? All of these laws shown here in the previous section were for two-sided limits, right? These were all for just general limits as x approaches a in general. Well, yes, but a one-sided limit is the exact same concept and meaning as a two-sided limit in every way, except that it's actually simpler and less restrictive. So, like, remember, all of these laws, we talked about, they only apply if the corresponding limits exist, right? Like, you can't apply these sum rules or this product rule, etc., unless the corresponding, all of the corresponding limits exist. This limit of f of x needs to exist, as well as this limit of g of x needs to exist. Okay, well, obviously for a general two-sided limit, it might be the case that one of these limits doesn't exist, and that might be the case for a one-sided limit as well. But if you think about it, for a one-sided limit, there's a better chance that all of the corresponding limits do exist. And then you can apply the rule. And why is that? Well, because one-sided limits are less restrictive. You don't have to, the limit, with a two-sided limit, the limit coming from both sides needs to exist and be the same, right? Well, with the one-sided limit, you're just looking at one side. And so again, these laws extend with no issue to one-sided limits. And it might seem like it would be more complicated dealing with a one-sided limit, but it's actually the opposite. It's much less restrictive. Like, for example, if you were dealing with a one-sided limit that involved an absolute value in the limit function expression. Let's say we had the limit as x approaches 3 from the right of the absolute value of x minus 3 over x to the 5th. Okay, well, the one-sided part of this limit is great because since we're only considering values of x that are greater than 3, then the expression inside of the absolute value, the x minus 3, is always positive no matter what. So we can simplify this by just removing the absolute value. And like if this, let's say this limit was approaching 3 from the left, well then since x minus 3, that expression is always negative for any of these x values, well then we simplify the absolute value expression like this. We can get rid of the absolute value. Right? And then like from here, you could do the quotient rule, like distribute the limits, the limit to the numerator and denominator, and then you've got the limit as x approaches a number of just polynomial expressions. You could do direct plug-in, but we could also just do a direct plug-in straight from here because this is a rational expression. And that's what you would do. You just plug 3 in. 3 minus 3 is 0, divided by 3 to the 5th is 0. This would also be 0. And if you're scratching your head a little bit thinking, why can we just automatically apply the direct plug-in rule here? right? I just plugged the 3 straight in both of these cases, right? Because that property, this property here, was only discussed in relation to a general two-sided limit. If f is a polynomial or a rational function, and a is in the domain of f, then this is only talking about a two-sided limit. So how could we just automatically go ahead and apply this property for a one-sided limit? Okay, I encourage you to think about on your own why automatically extending all of these limit rules, all of the properties about limits, the analysis about limits, the definitions of limits, from general two-sided limits to one-sided limits is trivial. And in fact, the laws are actually more flexible in regards to one-sided limits. Okay, so coming back to this example 3, again, we have this limit as x approaches 0 from the right of the principal square root of x is equal to 0. We want to prove that this limit is true as stated here using the precise definition of the right-handed limit. So, okay, how do we do this? Well, it's the same idea. We're going to guess a delta and then prove that the guessed delta value works. But first, we need to state the precise definition of limit inequalities in terms of this specific problem. That's what they do here. That's where we're going to start. So, okay, based on the right-handed limit, let me bring the right-handed limit definition up here. Okay, in this case, the limit point is 0. So, yeah, 0 here, 0 here. So there's the input delta restriction. Now, the output inequality, f of x is the principal square root of x, and L is 0. So there we go. And now what they do is they simplify this. So we haven't changed the input, but now the output, you apply the subtraction from 0, but then you can remove the absolute value because the principal even root is always positive. The output of any principal even root can never be negative. So, okay, there we go. There's the problem statement. We need to show that this is true in order to prove this limit. Okay, so once again, what we want to do is we want to start with the output inequality, and the goal is to manipulate the output inequality without changing that inequality as much as we can until we can relate the output inequality in some way to the input inequality. So if we take this and square both sides, and note that we're able to square both sides of this inequality with no issue in changing the inequality, since both sides are always positive. Epsilon is always positive, and so is the principal square root of x, right? Because like algebraically manipulating inequalities can be tricky sometimes. If you multiply or divide both sides of an inequality by a negative number, you have to flip the inequality, right? So it's hard to just start multiplying both sides of an inequality by an x expression or squaring both sides, whatever, because x can be, usually it could be negative, the whole expression of x. But in this case, it happens to not be an issue because epsilon is never negative and neither is the principal square root of x. So we can go ahead and square both sides, and we update to this. So we haven't changed the input restriction, and now the output we haven't changed the output inequality from the beginning, from here, and this is the output inequality. X is less than epsilon squared. Okay, and now there we go. We haven't changed the output inequality, but we put it into a form that we can relate to the input inequality. Specifically, both the input and the output inequalities are in terms of x. Okay, well, now from here, it's obvious that we should guess a value of delta that's equal to epsilon squared. And again, why is this obvious? It's because this is still 100% the original output inequality statement. We just algebraically manipulated this inequality to this form. It looks like the input inequality, but it's not. And so coming back to the original question, this is what we're ultimately trying to prove, that these two inequalities are simultaneously satisfied, and we've just put this original question, this original double inequality, into a different form, into this form. That's it. And so if we choose delta to be equal to epsilon squared, well, then obviously the input is satisfied. The input inequality is always satisfied. That's just the part of the problem statement we make. Okay, but based on the delta we choose for the input, will the output inequality also be satisfied? Well, if we choose delta to be epsilon squared and we're saying that x is less than epsilon squared, well then yeah, definitely. Okay, and then now step 2 is like a formality. We pretty much just verbally proved the limit, but we'll show this formally in step 2. So if we choose delta to be equal to epsilon squared, then what does that mean as far as the output inequality? Well, okay, here's the output inequality. We know that this can be simplified to this point. The principal square root of x is less than epsilon, but we can take the principal square root of the entire input inequality and get that the principal square root of x is less than the principal square root of delta. Now, how are we allowed to take the principal square root of this entire inequality without changing the inequality or having to think about flipping the inequality symbols? Well, because x is restricted to just the positive side of 0. So x is never negative, and then neither is delta by the definition of delta. So since both sides are always positive, we can go ahead and do this. Okay, but now we guessed that delta was equal to epsilon squared, so we substitute in epsilon squared. The principal square root of epsilon squared is epsilon. We don't have to put the absolute value on the epsilon because epsilon is always positive, right? The principal square root of x squared, if x can be any number, positive or negative, is the absolute value of x, but here we don't need an absolute value. And there you go. If we choose delta to be equal to epsilon squared, then the output inequality, the square root of x, is less than epsilon. So the output inequality is satisfied. And so, but like we can choose epsilon to be whatever we want, any positive number, it doesn't matter, no matter how small. And then when we square that number, we'll get delta. Or you can go the other way. You can choose delta to be 0.000 quintillion zeros 1, and then the corresponding epsilon is going to be the principal square root of that delta. And so that proves the limit. Okay, let's do another limit. Here's the limit as x approaches 3 of x squared is equal to 9. This is a general two-sided limit. We want to prove this limit. So once again, how did they get that this was equal to 9? Well, this is just a polynomial, so you can use the direct substitution property. 3 squared is 9. Or this easily applies to this property here, with n being equal to 2. The limit as x approaches a of x to the n is equal to a to the n. So we just put a here and n is 2, right? 3 squared is 9. Okay, but now let's go ahead and prove, based on the precise definition of the limit, that 9 is in fact the limit as x approaches 3 of x squared. So we want to work with the output inequality, and like it says, the goal is to connect the output inequality with the input inequality. But now, okay, well, first, the first step is you set up the precise definition of the limit inequalities. So we've got, for the general two-sided limit, here's the precise definition of the limit. So we're going to come to these inequalities here, plug in the a value, the f of x, and the L. So a is 3, f of x is x squared, L is 9. So there's the inequalities. And then there's delta is any number greater than 0, and epsilon is any number greater than 0. So we need to prove that these two inequalities are satisfied simultaneously. All right, so to connect the absolute value of x squared minus 9 with the absolute value of x minus 3, they first factor x squared minus 9 into x plus 3 times x minus 3. Then there's a property of absolute values where if you've got the absolute value of a times b, then you can just distribute the absolute value to each term, assuming a and b are real numbers, and these are real numbers for all x. So they apply that property of absolute values, and so now we've updated the pair of inequalities as shown here. Okay, now we're close. We've got an absolute value of x minus 3 here and an absolute value of x minus 3 here, but we still have this absolute value of x plus 3 mixed in with the output inequality. So what they do is they get really flexible with the absolute value of x plus 3 because we really don't care what the absolute value of x plus 3 is. We would like to just mix this term here in with epsilon, because epsilon is just a completely arbitrary constant, right? So it says if we define another arbitrary positive constant c such that c is defined in that c is greater than the absolute value of x plus 3, then we can make this statement here. The output inequality absolute value expression here must be less than c times the absolute value of x minus 3. Right? Assuming this c does exist in all circumstances for any delta we pick, that c exists according to this definition, then we can write this. Right? Because if c is always greater than the absolute value of x plus 3 for all x, and here all we've done is just replace c with the absolute value of x plus 3. So you've got the absolute value of x plus 3 times the absolute value of x minus 3 here, and then you got c times the absolute value of x minus 3. Well, if c is always greater, not greater than or equal to, always greater than the absolute value of x plus 3, then this is going to have to always be greater than this, right? Okay, and so what we're trying to do is we're trying to make sure that the whole proof is centered on this being true, right? This is just, this is the main output inequality, just in a different form. And so we're wanting to, like, this needs to be less than epsilon. This needs to be less than epsilon, right? This, for the output inequality to hold true, this needs to be less than this. Okay, and so if we can show that this is always less than epsilon as well, then we've automatically showed that this is less than epsilon. Okay, so what are the conditions of C that would make this true? That would make the C times absolute value of x minus 3 always less than epsilon. Well, okay, if this is going to be true, if C times the absolute value of x minus 3 is always going to be less than epsilon, well, then if you divide both sides by C, that means this is going to have to be true. The absolute value of x minus 3 is going to have to always be less than epsilon divided by C. And now, there we go. Now we've got a relation. We have the absolute value of x minus 3 here and the absolute value of x minus 3 in the input. Now we've got at least some portion of how the output inequality works related to the input inequality. It just needs to be the case that this positive constant C needs to exist per the definition for any delta that's chosen, but then at the same time, this needs to be true. This inequality needs to hold as well. If those two things happen, if C does exist for any delta and this inequality holds, then this inequality holds, the main output inequality, this. Okay, but what we can see then is that what this suggests is that we should choose delta to be equal to epsilon divided by C, right? If delta is epsilon divided by C, then obviously the input inequality holds for whatever delta we choose, but then if we choose delta to be epsilon divided by C, then this is always going to be true. Okay, but we're obviously not done yet. This is still a little bit confusing. There's a lot going on here. We haven't proven the limit yet, and the reason is because we've introduced this new variable C. We need to show that C does exist as defined for any delta that is picked. Yeah, it's nice. This is automatically going to be true if we pick delta to be epsilon divided by C. Great. But we need to talk about C here. How do we know that this is going to be true? There's always, no matter what delta is picked, there's always going to be some positive number C that is greater than, for any x that comes from this input, that's greater than the absolute value of x plus 3 in all cases, in all circumstances. So, okay, let's think about this. Let's think about C. So again, we define C to be as shown here. And once again, the question that needs to be answered is, for any given set of input values given by delta, given by this input inequality, if we plug any of those inputs into the absolute value of x plus 3, will there be some upper bound on all of these numbers? Some upper bound number C. All right, so let's think about what exactly is the input inequality. Well, we know it's, so in this case, we've got, so all this is you have, so all this is, it's a set of x values that's roped off on the number line. that these x values are centered about x is equal to 3, and it's all x values that are plus delta and minus delta away from 3, but not including 3 itself. So all of these x values, not including 3, where this distance is delta, this distance is delta. Okay, so we're thinking about, okay, now what are all of the, if we take all of these x values and input them into this expression, the absolute value of x plus 3, what happens? Well, okay, we first just, with the x plus 3, we're just shifting all of these to x is equal to 6. That's the first thing we do, okay? Now, the next thing we do is we just take the absolute value of all these x plus 3s, but that doesn't do anything. They're all positive anyway. So there you go. This is the absolute value of x plus 3. So the question is there some number c that's a ceiling on all these values? Yeah, this, which we can see is just 6 plus delta. That's c. Okay, so there you go. For any delta value that's chosen, absolutely any delta value that's chosen, this positive number c will always exist, and it's given by 6 plus delta. And now, so that's it. We're done. We've proven the limit. Well, I mean, actually, let's go through the part 2 and sort of the whole formality to show that the limit is proven. Let's do that. So for this limit to be true, the limit as x approaches 3 of x squared is equal to 9. For that statement to be true, these two inequalities need to be satisfied simultaneously. Therefore, we guess that delta is equal to epsilon divided by c, where c is some new variable that we've introduced into the problem. C is a positive constant that satisfies this inequality. The absolute value of x plus 3 is always less than c, where c is just, now this is a new inequality that we've added to the problem in addition to the output inequality. This needs to be also satisfied as far as in relation to any input coming from the input inequality. Okay, now what we showed is that what this inequality does is if we apply this to the main epsilon output inequality, then assuming that c, that there's all, for any delta that's chosen, this c exists as shown here. If that's true, then also assuming that this inequality is true, this also needs to be true. Here's now a fourth inequality that needs to be satisfied. So we have the input, the epsilon, this, and this. So if this is true, in addition to c always existing, then this is going to be true. Okay, but based on what we chose for delta, this is automatically true. We chose delta to be epsilon divided by c, and this is related to the input. And then now, but we already proved that this is true no matter what. There is this c that's true no matter what. And there you go. That's it. We're done, because now we can just pick any delta we want, and there's going to be a corresponding epsilon. Let's come back here. We can pick any delta we want, and there's going to be an epsilon that corresponds to that delta. And we can actually solve for delta in terms of explicitly just epsilon, because we could say that, okay, we've defined delta to be equal to epsilon divided by c, but c is delta plus 6. So we've got that this delta is equal to, or no, it would be, this is epsilon. Okay, so now we could just solve this for delta. So let's see, if we've got x is equal to, let's do, okay, well, y is epsilon, so, and delta is x. So now x is equal to this. Now let's solve this for x. Okay, but now delta is always positive, so there we go, this. Delta is equal to the principal square root of epsilon plus 9 minus 3. And there we go. So we could pick any delta we want, and there's going to be a corresponding epsilon to that delta. No matter how small, we could pick delta to be anything, no matter how small, or we can go the other direction. We could pick an epsilon first, and there's going to be a delta, where delta and epsilon are any positive number. So, okay, now, so it says here in this paragraph that obviously this last example was pretty involved to prove the limit. And this was still a simple limit problem, just a basic single term second order polynomial, right? Still really simple, just the limit as x approaches 3 of x squared. That's really simple. So as the functions get more complicated, you could imagine this process would obviously get a lot more difficult to try and explicitly prove the corresponding delta and epsilon inequalities. But this isn't, in reality, this isn't how limits are proved. Instead, basic limit laws are proved using the precise definition of the limit. Then more complicated limit laws are proved from these basic limit laws, using these basic limit laws as a starting point. And then actual limits themselves are proved through the limit laws, right? So like the foundational limit laws here are proved using the precise definition of the limit with epsilon and delta. Once these are proved, then you can use these as a foundation to prove more complicated laws. And then from there, when you're dealing with an actual limit, if you want to prove an actual limit, you don't have to go through the whole, everything we've been doing. You just use one of these limit laws. You use the direct substitution property, for example, or you use this nth root property. You take the nth root out of the limit. And so here they just give an example of how the sum rule is proved, where you can distribute the limit to each of the limit as x approaches a of f of x plus g of x is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. They show how this is proved here using the precise definition of the limit, the delta and epsilon. All right, now we can also think about the precise definition of infinite limits, which remember is a limit that goes to infinity. The limit as x approaches a of a function is equal to positive or negative infinity is an infinite limit. So once again, you've got a function f defined on some open interval that contains the number a, except possibly at a itself. So this is a general two-sided limit. Then the limit as x approaches a of f of x is equal to infinity means that for every positive number m, there is a positive number delta such that if delta is constrained by this inequality, then f of x is greater than m. Okay, so you can notice how the delta inequality is defined in the exact same way as the original general two-sided limit that we started with. It's exactly the same. You just got this interval of x values that are delta above and below the limit point a, but not including a itself. Same exact idea for an infinite limit, right? Here we're just at the moment thinking about a limit that's going to positive infinity, but in a second we'll talk about a limit that goes to negative infinity, and it's still going to be exactly the same, the input interval, assuming it's a general two-sided limit. And so the main difference is with the output inequality. If you noticed that there's no epsilon in this case, in this definition, it's just this positive number m, capital M. And there's no epsilon because a single finite output value L isn't being constrained. Remember, this limit actually doesn't exist. Infinite limits don't exist. We're not approaching a finite single number. All it says is that for this limit to be true, for any f of x, you can plug in any x value that corresponds to this delta inequality, and for no matter what x value you plug in, the function is going to be greater than some value m, some just random positive number m. So what does that mean? Well, since m is any positive number, doesn't matter what it is, the idea then is from the whole infinitely powerful calculator perspective, m can be made as large as you want. Just by making x approach a however close you want, which would be based on what you choose delta to be. Approach A from either side. And so the infinity comes into play because M can be as large as you want. You could say, okay, I want this to be satisfied. I want to be sufficiently close to A on both sides of A to where the function output is always greater than, for any of those x values, greater than 100 quintillion. You can do that. There's going to be a delta that corresponds to M being 100 quintillion. And they show this graphically here. You've got a delta on both sides of A, and then for any of the x values in that interval, except for x being equal to A, the function on either side is always greater than M. Always. Again, coming from both sides. Okay, so let's think about proving that the limit as x approaches 0 in general of 1 over x squared is equal to infinity. We know that, so in 2 sections ago, we learned how to work infinite limits like this. We know that coming from either side of 0, as you get closer and closer to 0, the denominator is becoming a smaller and smaller positive number. And so if in the numerator you've got 1 doesn't change for any x value, and then you're dividing 1 by a smaller and smaller and smaller positive number, the output is going to be getting larger and larger and larger. And again, this same behavior is happening from either side. So the limit is equal to infinity, positive infinity. Now, from a precise definition of the limit standpoint, it does intuitively seem as though this limit is equal to infinity. The reason is because it seems as though we could specify as large of a number as we like, for example, a number like 100 quintillion, and with a hugely powerful calculator, we could find a corresponding distance from 0 on either side of 0, where if you plug either of those very small values into the function, the output will be right around 100 quintillion, and then if you got any closer to x from there, it's just going to be a larger number than that. But the goal is to officially prove this. So, okay, if we write out the criteria for this infinite limit, so A is going to be equal to 0, and f of x is equal to x squared. So they write out the 2 inequalities that need to be satisfied simultaneously. Now, we go through the same process as we did with non-infinite limits. We're going to start with the output inequality, and then the goal is to manipulate this inequality to the point where we can relate it to the input inequality. So they start by taking the reciprocal of both sides of this inequality, which we don't have to worry about complications here since 1 over x squared and m are always positive. So they take the reciprocal, but then they flip the inequality as well. All right, now they can take the principal square root of both sides. Again, both sides are always positive. They take the principal square root of both sides. Now, but since x squared is always positive, but x itself can be positive or negative in this case. So the principal square root of x squared is the absolute value of x, right? Because it's like if x was minus 5 squared, the principal square root of that is not minus 5, it's the absolute value of minus 5. So you need the absolute value, and now they distribute the square root on the right side to the denominator. Okay, and there we go. Now we can directly relate the output inequality to the input inequality with this absolute value of x. If we choose delta to be equal to 1 over the principal square root of m, then the output constraint will be automatically satisfied. The output inequality, because this is the output inequality. We just put the output inequality into a different form, right? So if delta is 1 over the principal square root of m, in which case the absolute value of x is less than 1 over the principal square root of m, well, the output inequality is automatically satisfied. And since m can be whatever we want, any positive real number, delta can be whatever we want. So that proves the limit. Okay, now a limit that goes to negative infinity is the exact same idea. Again, you have the same input delta interval. The only difference here in this case is that we're going to have some negative number, capital N, to where if you take any of these x values and put them into the function for all of those x values will be less than capital N. That's what they're showing here. Your delta away from A, there's some negative number N, capital N, to where if you got closer to A from delta away from A, you're just going to be getting more and more larger in magnitude negative numbers.